In the last video, we looked at the colligative property of boiling point elevation. We saw that as you add a solute to a liquid, its equilibrium vapor pressure lowers because it is harder for those water molecules to escape to the gas layer. Now, in turn, we will see a lower equilibrium vapor pressure at the same temperature that a pure solvent would be at. So, what do we have to do in order to boil this solution with now a liquid and a solute inside of it? We would have to raise it to a higher temperature to get enough gas particles to equal our atmospheric pressure. So we saw that the boiling point will go up. Well, how do we solve for how high this boiling point is going to be? It is a very simple formula. It says the change in temperature boiling. So this is going to signify that we are going to go up. The change will be higher than our normal boiling point, is going to be equal to KB, which is the boiling point constant. We call this the boiling point elevation constant. Right? This is going to be specific for each liquid. So this would be from a data table. This is discovered when someone ran this experiment. You would never be required in any chemistry class to memorize all of the boiling point elevation constants for every liquid out there. This is something that would be provided for you, or if you were given all the other variables in the equation, you could solve for it. And the only other term in this equation is MC, which is the colligative molality. This is colligative molality. Remember, this is equal to the molality times the I factor, right? And if we're thinking about units, this is going to be our colligative molality is moles over kilograms of solvent. This is going to be our boiling point elevation constant is in the units Kelvin times kilograms over moles. And we see that these units cancel out nicely. The kilograms cancels out, the moles cancels out. We are left with the unit of Kelvin, which is exactly what we want. We want the change in temperature boiling, the temperature in Kelvin. So using this formula, we could plug in our boiling point elevation constant, and we could plug in how many moles of solute we have, keeping in mind the I factor, divided by the kilograms of solvent we have, so how much water or how much of a liquid we have. And when we plug that in, that would tell us the change in temperature boiling. So if the change was 3 degrees Celsius and we're dealing with water, the new boiling point with that much solute in it would be 103 degrees Celsius, because that's the change. So this is how you solve for boiling point elevation.